Hello everyone, welcome to my YouTube channel where we discuss about programming languages and other funny stuff. Today we are going to take a look at the QuickSort algorithm and how to make it easy using the functional programming paradigm. So let's get started. We will start by taking a look at the QuickSort algorithm written using the Java programming language. I am not the author of this piece of code. I've taken this from geeks4geeks.org, so all credits goes to those guys who are making an awesome work. While this piece of code is running perfectly, both in terms of performances and beauty of code, I personally believe that it would be a bit hard for me to explain to you what QuickSort is by reading this solution. And not because it's written in Java, not because it's imperative, but because it's really hard to understand what this code does by just taking a look at the methods and all the variables and how we do instantiate them and how we manipulate them during the execution flow. So let me show you how to implement the same algorithm using recursion without using variables at all and using a declarative approach rather than imperative one. And we will do that by using Haskell. So before moving on with the Haskell implementation, please keep in mind that I'm not comparing performances or beauty of code. I'm just comparing two different approaches. So yeah, let me reveal to you a 6-line solution for the same algorithm, but in Haskell. And here it is. So when I'm talking about declarative programming, I'm referring to a way of writing code that describes the data that we want as output for our computation rather than a procedure for obtaining a certain result given some data. And I find this particular QuickSort algorithm implementation to be an awesome way for showing you what declarative programming is. So let's start reading this 6-line long implementation in Haskell. So we will start by writing the type for our QuickSort function. And this function will take a list of A and returns a list of A as a result. And A is a generic type such that is a part of the ORD type class. The ORD type class is a group for every single type that is orderable, so integers, floating point numbers, and so on. Then, if we are passing an empty list to our QuickSort function, we will return again an empty list. This will be really important when we'll be applying recursion to this function because it will act as an exit point for recursion. When we are passing a non-empty list to the function, we will destructure it by taking the head and the tail of the list itself. The head is just the first value inside of our list, and the tail is the remaining part for our list, of course. And then we are taking all the number that are less than our head using list comprehension. If you have some experience with the Python programming language, you may be already familiar with the list comprehension. But if you're not, let me explain this to you. We are declaring a new function which is called smaller. I know this looks like constant or a variable, but it's not. We don't have variables and constants in Haskell. We only have definitions or functions. And in that case, we have smaller, which is a list. We are referring to the single element of the list by using the y abstraction in that case. And yeah, every single element of that list must be less than x, which is the head of the original list. And we are doing the same for bigger, which is the other function that we are going to create inside the QuickSort body. And in that case, y must be greater than or equal to x. So we are basically dividing our original list into two different lists. One containing all the numbers that are less than x, and the other one where all the numbers are greater than or equal to the head of the original list. So that said, we are basically returning QuickSort of smaller. So we are applying QuickSort itself to our smaller list, and we are concatenating the result of that expression to x, which is the pivot value for that case, and we then concatenate this to the result of QuickSort of bigger. So as you can see, we're using recursion instead of loops and other stuff for computing the result of the QuickSort function. Now let's try to run this and see if it works. Yeah, it's working. Now you may be thinking that I'm cheating, and that's only possible to achieve such a simple solution using Haskell because of, of its syntax and its rules, but that's not true at all. I'm going to show you 3 different solutions using 3 different programming languages. And the first solution that I want to show you right now is with Python. So as you can see, the Python solution is actually really close to the Haskell one. And we are basically doing the same steps. So if we are passing a list where the elements count is equal to or less than 1, we return just the list. And this will be the exit point for recursion. And then we are using list comprehension, once again, for taking smaller, and list comprehension for taking bigger, which are the 2 lists where we're going to apply QuickSort recursively on. Then we're going to concatenate the result of these 2 function calls to the pivot value, which is the first element of the original list. And let's try to run this. And as you can see, this is still working. Now let's move on to a JavaScript implementation using the same concept that we've seen so far. So as you can see, this is still a very neat implementation for this algorithm, and we are basically repeating all the same steps that we've seen before. So if you are passing an empty list as an argument, we will return an empty list, of course. This will be the exit condition for recursion. And then we are extracting x and xs, just like we've seen before. Then we are creating smaller and bigger. We don't have list comprehension in JavaScript, so we are using the filter method for extracting all the numbers that are greater than or less than the x value, which is the pivot. And then we are returning QuickSort of smaller and QuickSort of bigger once again. And we are concatenating those 2 results with x, which is the pivot value. Let's run this. And it's working. Now let's move on with the last solution for today. And we're going to implement this algorithm using Elixir, which is a functional programming language that compiles Erlang bytecode. And I highly suggest you to take a look at how beautiful this language is. So I find this to be the easiest solution for today, as if we are passing an empty array, we will return an empty array. And I should have said list because Elixir doesn't have arrays. It has lists, I'm sorry. But if we are passing a non-empty list, we will take x and xs just like we've seen so far. Then we are going to use split with. So basically we are passing xs, which is the tail of the original list, and we are splitting in 2 different lists where the first one will contain all the numbers where every single number of the original list is less than x, which is the head. And the second list, of course, will contain the remaining part of the original list. Then we are going to apply QuickSort recursively, just like we've seen so far. And that's it. It's really, really easy. Let's run this. And it works. So that was all for today. I really wanted to show you how to write algorithms using a declarative approach, because I know that sometimes you may be stuck with the traditional approach, the traditional imperative approach, I mean. And using a different approach for solving your problems sometimes can be really helpful. So I really hope you enjoyed this video. Please use the comment section below for showing me your favorite implementation for this specific algorithm in other languages if possible, and see you next time.